We are now moving from laminar flow to turbulent flow, and there's a couple important differences. Laminar flow, as the name implies, is flow sort of in sheets. You have this relatively steady flow in the y direction. There's really not much happening in y, and that's because of the conservation of momentum. There's just a much larger gradient in y than there is in x, and so you see this, the y component of velocity is very small. When we get to turbulent flow, that's no longer true. Right? You start to see that at any point along the surface, you get a lot of y movement, a lot of eddies that are forming, a lot of momentum transport, and that really changes how we have to model the flow. So let's go through and understand how we get to turbulent flow, how we characterize it, and then what it sort of implies in terms of heat transfer and shear stress. So first, let's sketch out our surface and look at how a boundary layer is going to develop. So if I have some surface here, and I have u infinity coming in from this side. Let's see, my coordinate here is y, my coordinate here is x. And I were to draw the boundary layer, it would look something like this, right? You start at, let's draw it in green. So you start at 0 thickness, and it sort of grows with the square root of x. So this is my laminar boundary layer. Again, the boundary layer thickness is delta sub m, I guess we'll use here for momentum. And then if you look at what's happening here, we have this boundary layer that's growing. And if you approximate the shear stress in here using the boundary layer thickness as part of your gradient, what's eventually going to happen is that the shear stress that's involved gets smaller and smaller and smaller as delta m grows. And eventually that shear stress is small enough that the sort of fluctuations or random fluctuations in the fluid are no longer, let's say, muted out by that shear stress forces. And the momentum will start to cause these instabilities. And it will then become turbulent, right? You start getting these eddies and disturbances that form. So it all comes down to the fact that you have this delta m that's growing as a function of position. So in flow over a flat plate, that's going to occur at some position x. It will just inevitably occur because the boundary layer, laminar boundary layer thickness continues to grow as a function of position, right? So if we wanted to anticipate where that is, let me actually do one thing here. So if we sketched out what that shear stress looks like at the very leading edge, here I'll do it in a different color. The very leading edge, that's going to be infinite, right? This up here is infinite, and it sort of goes down like this, right? continuing to decrease. So at some point, that shear stress here, tau s, gets to a low enough value that the forces sort of flip. So okay, if we wanted to predict where this would happen, we would use the Reynolds number to do that. So we would say, just defining our Reynolds number, Reynolds is equal to some u characteristic times L characteristic rho over mu. Right? And if you look at this, this is proportional to the inertial forces over the viscous forces. Right? For our flat plate, it is Reynolds, where x is the characteristic length, is equal to u infinity times x times rho over mu. So I guess if we wanted to know at what point the shear stress becomes small relative to the inertial force, we could just do that by looking at those specific contributions. What I mean is, let's take an inertia. So an inertia would be rho times u infinity squared, or it's at least proportional to that, where viscous forces are proportional to mu times u infinity over delta m, at least according to our approximate model. So we want to look at the ratio of these two things. Okay. So if I take the ratio of those two things, I I would get, let's see, rho u infinity squared delta m over mu u infinity. So u infinity cancels out. And this tells us what? Reynolds in terms of delta m is equal to rho u infinity delta m over mu. OK, so we kind of danced around there and got something, but it's important. What is this little ratio of these two things telling me? It's telling me, actually, if I want to compute the Reynolds number for instability is related to delta m. Right? It's just what we've been saying. So, and really, like in a bigger picture, that's what the Reynolds number is. It's always some relationship between the inertial forces and delta m. It's just that when we write it out for like a pipe or for a flat plate, we don't actually know delta m to begin with. We want to have it in terms of some other characteristic length. So we use x, or we use the hydraulic diameter, or whatever. But in reality, Reynolds is sort of conceptually this relationship between the inertial forces and delta m. OK, so if we want then to characterize where this becomes unstable, you can go to maybe empirical type relationships, but it turns out that Reynolds delta m is approximately, becomes unstable at approximately 3,500. I just say this is unstable, or transitions. So Reynolds delta m 3,500. We got this from a flat plate relationship, right? But maybe you have had fluids before and you recognize this number, right? Anybody recognize this? Where else this number shows up? It would be, well, in what situation does this show up, I guess, other than a flat plate? So if you were to go to a correlation for internal flow, right, like a duct or a pipe or something like that, you always say, OK, my critical Reynolds number is about 3,600, right? That's about where flow transitions from laminar to turbulent. So, but this is for a flat plate. But that actually makes sense if you think about it. So Reynolds in terms of delta m, 3,500. What's happening in internal flow? In internal flow, you're having two boundary layers that sort of collide with each other, and then they stop developing. So what is the maximum boundary layer thickness in a duct? It's related to delta m. Delta m is related to the hydraulic diameter, right? It's going to be a property of the sort of available area before things collapse on each other. So it's not an accident that 3,500 is the same for this relationship as it is just in terms of hydraulic diameter. Okay. So that's let's say the transition based on delta m. I guess what we want to do then is kind of relate this back to our position for a flat plate and maybe get some critical Reynolds number for flow over a flat plate. So let's go to the next slide here. So let's draw, again, a little sketch of our situation here. We have a flat plate. We have a boundary layer that's growing. So we start here. And then at some point, the flow sort of begins to become unstable. So we would say at this point here, where it just becomes unstable, that's our delta m critical. That is the thickness at which those shear forces and momentum forces sort of have that ratio of 3,500. Let's draw a few other things while we're at it. So we have, again, u infinity. This is our x position. And then we have a y coordinate here. So this region to the left is laminar. This region is turbulent. And again, what we want to do is relate the knowledge that the transition happens at 3,500 to something that has to do with the coordinate x. So let's write out our formulation. RE delta m critical equals 3,500. And that we said was rho u infinity delta M critical divided by mu. So rearranging this and solving for delta M, we just get delta M critical is equal to mu over rho u infinity times RE delta M critical. Right. So that gives us a thickness at that point. Once we have that, if we have some, let's say, relationship for delta M, then we can enforce that. So if we know that, let's say, we want to use the Blasius solution, so delta M critical over x is equal to 4.916 over the square root of Reynolds, which is a function of x, we can then tie these two things together to tell us how the critical Reynolds number relates to x. Okay, so then just doing the algebra here, we would see, let's see, write this out. So I'm going to use this relationship and say rho, that's not a bad rho, try that again. Rho times u infinity delta M over mu. So this would be rho u infinity over mu times this substitution 4.916 times x over the square root of Reynolds x. So simplify this. Let's see. So what are we doing? So we have a Reynolds number here, rho u infinity x over mu, that's Reynolds x, over the square root of Reynolds x times 4.916. And that just simplifies down to 0.041 times square root of Reynolds x. Oh, sorry, I skipped a step. 4.916 times Reynolds x. Now if we want to use the relationship in terms of delta M, we would equivalently write this as REx is equal to 0.041 RE delta M squared. So that should just be algebra. But these are sort of equivalent ways of writing it. We've just related it to delta M. OK, so if we know that, and then we know the critical number is 3,500, we can substitute in, and then we'd say Rex critical is equal to 0.041 times 3,500 squared, and that equals 5 times 10 to the 5th. Right. OK. So this is probably a recognizable number as well. That's your transition to turbulence for flow over a flat plate where Reynolds number is defined in terms of x. Right. So it turns out mathematically it's equivalent to say this or this, right? It's just a matter of defining the Reynolds number appropriately.